spherical coordinate system. So with the spherical coordinate system, so you construct it using the Cartesian coordinate system like this, okay? And then here you define rho, so the magnitude of this vector rho. In the unit vector, what is the unit vector in this direction? The unit vector e rho, okay? Then you also define your angle phi. Then you indicate the vector, the unit vector, which we call e phi, in the direction of phi, okay? This direction like this. So these vectors are such that e rho, the unit vector e rho, is perpendicular to e phi. So what is the importance of knowing this property? You know that when you find the derivative of e rho with respect to phi, it will give you a vector perpendicular to e rho, that is e phi, okay? So once we found e rho to be cos phi e plus sine phi g. Therefore, we can deduce that if we, once we derivate this with respect to phi, is going to be negative sine phi in the direction of e plus cos phi in the direction of g. So these are the two unit vectors that we found from other coordinate systems, such as the polar coordinate system. So you can look at the video on the polar coordinate system on how we find these two, okay? Or in other simple ways, it's very simple to find e rho, because e rho is a unit vector in this direction. So because it's a unit vector, this direction, this adjacent side, we said according to this adjacent side will be equal to cos phi, then the opposite side will be sine phi. So if you want to know this distance, you go this way and you go upwards. So therefore, e rho is equal to cos phi in the direction of what? E plus sine phi in the direction of g. Then you can find e phi. You can deduce e phi from finding a derivative of e rho, which is going to give us negative sine phi e plus cos phi g. So you can look at my previous video, the polar coordinates, on if you want to understand further on how we found e rho and e phi. So this is just a summary on how we found that. So once you, let's now create the spherical coordinate system together. So the spherical coordinate system, here is how we create it. So you're going to use the Cartesian coordinate system like this, and then you're now going to use rho, okay, mark this radius of rho, then e rho like that. Then of course we've got phi here, okay. Then this is e phi, such that these two are perpendicular. Then you're also going to add r, okay. You're going to add the vector r in the direction of er, okay. Then you're going to add phi. Now phi is going in this direction, so you're going to define such that they are perpendicular to each other. You're going to define a new unit vector e theta, okay. E theta, this angle is theta, so e theta. So here you had rho, e rho was associated to e phi. Then here er is perpendicular to e theta. So which means that if I find the derivative with respect of er with respect to theta, it's going to give me e theta, okay. So this, knowing that they're perpendicular to each other and knowing that er is associated with e theta, will help us know that when you have er, you can just find e theta just as we had E phi, we found we had E rho, we found E phi by derivating E rho with respect to the angle. We found this. Then in the same reasoning, we're going to find the derivative of ER with respect to theta to find E theta. Then you have with that you are going to have E rho, E phi, and ER and E theta. So the spherical coordinate system it's a system that uses the angle theta, r, and also the angle phi. Those are the three parameters that you're supposed to know from the spherical coordinate system. So the spherical coordinate system uses the parameters r, theta, and phi. So it's a two-angle system. So it uses two angles. So what is the unit vector in the direction of r? It's ER. Okay. What's the unit vector in the direction of theta? It's E theta. Then what's the unit vector in the direction of phi? It's E phi. Okay. So here we need to know how to find ER. Then we're going to, from ER, we're going to find E theta. Then E phi, we've already found it. From E rho, okay. So these are the unit vectors that you are going to be using, that the spherical coordinate system uses. So the most important thing here to know is knowing the parameters that the spherical coordinate system uses. So the parameters that the spherical coordinate system uses is the two angles theta and phi, and then the radius r. So rho is not used in the spherical coordinate system. This rho was used in the cylindrical coordinate system. From my previous video, you can check it up. So now let's find ER as a function in the base Cartesian. Okay, let's convert ER in the base Cartesian, in the Cartesian basis system. So now how are we going to do that? So here's what we're going to do. So now here, when you construct your spherical coordinate system, when you construct it, let me reconstruct it once more. Okay, so with a spherical coordinate system, which is like this, okay, then this is your rho, okay, then this is your r in the direction of AR. So notice that what you're going to have, this is in 3D, so what you're going to have this rectangle, okay, you're going to have this rectangle. Let me just draw it nicely. So let's say we have we are trying to construct a spherical coordinate system like this. Okay, if you have a system that is like this, then this is our rho and this is our r. Our r is positioned such that our study point is in 3D. The point, our study point, which is M. Okay, and then so we're going to have a rectangle as a result of this system. We're going to have a rectangle like this. Okay, we're going to have this rectangle, yeah, like this. Okay, so this rectangle, the angle here, this is theta, then the angle here is phi. Okay, then we said that this length is rho, then in which direction? E rho. Okay, then this length we said it was r, so in which direction? ER. Okay, now so we can now get this rectangle and we can project it here. So this distance, the rho distance, is the down distance. So this distance is rho. So and in the direction of E rho. Okay, then the upward distance, this is the z-axis. Okay, so this is in the direction of car. Car is used for the z-axis. Okay, so what is the length of this? We don't know. Then in between we have r. Okay, in between we have r in the direction of AR. Okay, then we also have this angle theta. So I'm projecting this rectangle, I'm projecting it here. Okay, So the main purpose of doing this is for us to know what this length is and what this length is, which is the same as this length because this is a rectangle. So this length is equal to this length is equal to this length. What we know so far is that this length is equal to rho in the direction of E rho. Then this length is equal to R. Okay. Now, so we're going to apply trig identities in the same way. We know that the opposite side of the angle, the opposite side is equal to r sine theta. Then the adjacent side is equivalent to r cos theta. So this is the adjacent side, this is the opposite side. But since this is a rectangle, this side will be equal to this side. So rho will be equal to r sine theta. So take note of this. So in the spherical coordinate system, wherever there is rho, you're going to be replacing it with the r sine theta. This is a very important fact to note. Okay. So from this projection, we found that this length, which was initially rho, is now converted to r sine theta. Because why? Because in the spherical coordinate system, we don't deal with the rho. We only deal with r, theta, and phi. So we convert everything that is not r, theta, and the angle phi. Okay. Now, from here, from this rectangle, we can, so our job here is to find ER. So this is the point O. So, and this is the point M. So how do you identify, how do you find OM in the spherical coordinate system? Very simple. OM is found by, if you have got a vector, you've got a magnitude, the magnitude was R, and the direction is ER. You just write R, ER, okay? Because you have the magnitude and the direction. So this is how you find the OM in the spherical coordinate system. Take note of that. So now we're trying to find an expression of ER in the Cartesian coordinate system as well. So we're going to equate these two. This is the same as, so instead of going OM, instead of me finding R, ER, I can also move in this direction. I'll move in this direction, then I'll go upwards. Okay. Now the question is, if I move in this direction, what is the magnitude of this direction? Let's say here it's, if this point is n. So ON, what is ON? So let me even write it, ON plus NM. Okay, so now the question is, what is ON? ON is, we found it, initially it was rho, but now we found that it's r sine theta. In which direction? In the direction of E rho. This direction, okay. Then plus, what is NM? NM is r cos theta. In which direction? Direction of k. We said that this length was in the direction of k. Okay, so this is very much important. So what are we finding? We're finding ER en fonction de EG et K. Okay, now from here we can factor out R. So ER is equal to, you factor out R, so you're going to have sine theta E rho plus cos theta K. Okay, so from here, from the left hand side to the right hand side, we can conclude that on peut conclure que ER is equal to sine theta E rho plus cos theta K. So this is how we find ER. So if you, as you can see here, we said that the spherical coordinate, the cylindrical coordinate system from my previous video uses E rho, Phi, and K. So this expression that we found here is the expression of ER in the cylindrical coordinate system. Why am I saying the cylindrical coordinate system? Because we're using E rho and K, which are the base vectors of the cylindrical coordinate system. Now our job is to convert ER in the Cartesian coordinate system, that is with the bases E, G, and K. Okay, so once you find an expression of ER as a basis